The alternator. This device is an essential part of every combustion engine vehicle's electrical system. So, what does it do and how does it work? That's what we'll be covering in this video, which is sponsored by Squarespace. Head to squarespace.com to start your free trial, or use code Engineering Mindset to save 10% on websites and domains. We find the alternator within the engine bay of the car. The shaft of the alternator is connected to the engine via a belt and pulley. When the engine is running, the shaft of the alternator is forced to rotate. This rotation generates electricity. An alternator looks something like this. The alternator produces a type of electricity known as AC, or alternating current, and this is why the unit is called an alternator. With AC electricity, the current of electrons flows forwards and backwards constantly. This is the same type of electricity that you will find in the power outlets of your homes, although the voltage in your homes will be much higher. However, all the electrical components within the car use another type of electricity known as DC, or direct current. With this type of electricity, the electrons flow in just one direction. This is the same type of electricity which we get from a battery. So, the alternator converts the alternating current into direct current via a rectifier. The output voltage of the alternator varies with the speed of the car. So the alternator also uses a regulator to limit this and maintain a near constant output. Every modern vehicle needs electricity to operate. This is used to power things such as the lights, the music system, electric windows, window wipers, etc. The engine combusts fuel. This is used to turn the crankshaft and propel the vehicle along. The engine only provides mechanical force. It does not produce electricity. So, we need a way to power all the electrical devices within the vehicle, and that's where the alternator comes in. Within the engine bay, we also find a 12-volt lead-acid car battery. This stores energy in the form of chemical energy. It does not store electricity. By the way, we have covered how the car battery works in great detail. Do check that out, links can be found in the video description down below. When the engine is off, the battery powers the car's electrical components. This will drain the battery though. When the car starts, the battery provides a huge amount of current to the starter motor, which turns the flywheel and starts the engine. The battery is again partly drained during the startup because of the large current required to turn the starter motor. Once the engine is running, the alternator is used to recharge the battery so that it can store energy to start the engine again in future. The alternator will also power the car's electrical devices while the engine is running. But if the battery is left to discharge for too long, then it will not be able to provide the large current necessary to start the starter motor, and so the car will need to be jump-started. Let's have a look at the main parts of the alternator. At the front of the unit, we find the pulley. This is a wheel which has grooves cut into it to help grip the belt that provides a rotational force from the engine. The pulley wheel is attached to the shaft which runs through the entire length of the alternator. The internal components are held inside the main housing. The housing consists of two parts, the front and the rear bracket. There are some slots cut into the casing to allow air to pass through and remove the unwanted heat which is generated. At the back of the unit, we have the electrical connections. There are many different designs, but this is an example of a simple 3-wire design with an internal regulator and rectifier which has the following terminals. First of all, there's the B terminal. This is the output of the alternator which charges the battery. Then we have the S terminal. This allows the regulator to sense the voltage. And then we have the F terminal. This is connected to the ignition and provides the initial power to the electromagnet during startup. To complete the circuit, electricity flows back through the car's frame to and from the battery's negative terminal. As this unit has an internal regulator and rectifier, we find these components at the rear end of the unit, which is usually under a protective cover. We'll see those in more detail a little bit later in this video. By removing the housing, we can see inside the unit. The first thing we see is the stator. The stator is stationary and does not rotate. This consists of a number of laminated sheets which have a pattern of slots around the inner edge. Then we find 3 separate sets of copper wires which are wound between these slots in a certain order. One end of each coil is connected together to form a neutral point. This is a star configuration. Each coil set will produce a single phase of AC electricity, providing 3 phases in total. The other end of each coil passes through the case and attaches to the rectifier. The alternator produces AC alternating current, but the battery and the electrical devices of the car need direct current. So the rectifier is going to convert the AC into DC electricity. At the center of the alternator, we find another coil of wire which is wound around an iron core and connected to the shaft. The shaft also holds 2 slip rings. The slip rings are connected to opposite ends of the coil. Within the rear housing, we find some brushes. These are some spring-loaded carbon blocks which are pushed outward to rub against the slip rings to form an electrical connection. The car battery initially provides electricity to the coil via the brushes. As the electricity passes through the coil, it generates an electromagnetic field. To enhance this electromagnetic field, 2 iron claws are placed either end of the coil, which will interlock with each other. One end will become the north pole and the other will become the south pole. As the electromagnet is attached to the rotor shaft, when the engine turns the shaft, it also rotates the electromagnet past the coils of the stator. This will cause the stator coils to generate, and so electricity is generated. Once the alternator is generating electricity, the alternator is able to power the electromagnet by itself via a diode trio, which converts the 3-phase AC into DC. The voltage and current produced by the alternator will vary with the speed of the vehicle. The faster the vehicle travels, the faster the crankshaft rotates, and so the faster the alternator also rotates. This increases the voltage and current. To control this, another component is used called the regulator, which is mounted at the rear of the unit. This is an integrated circuit board which monitors the output of the alternator and varies the current flowing through the electromagnet to control its strength. The strength of the electromagnet can be used to vary the output from the alternator. Electricity is the flow of electrons in a wire. The copper wire is made from millions and millions of copper atoms. Each atom has a free electron. This is an electron which is able to move freely between other atoms. It does move 2 other atoms by itself, but this occurs randomly in any and all directions, which is of no use to us. We need lots of electrons to flow in the same direction, and we do that by applying a voltage difference across the 2 ends of a wire. This forces the electrons to flow. If we reverse the battery, the electrons flow in the opposite direction. When electricity passes through a wire, an electromagnetic field is generated around the wire. If we place some compasses around the wire and pass a current through it, the compasses will align with the magnetic field. If we reverse the direction of current, the magnetic field reverses and the compasses change direction. If the wire is wrapped into a coil, the magnetic field becomes stronger. Each cross-section of wire still produces an electromagnetic field, but they combine together to form a larger, stronger magnetic field. The electromagnet produces a north and south pole, just like a permanent magnet. If we increase the current to the coil, the electromagnetic field increases. We can also do the opposite. If we pass a magnet through a coil of wire, a current is generated in the coil. The dial on the ammeter indicates a current flowing in the forward direction. This is therefore generating a DC or direct current. When the magnet stops moving, the dial returns to 0. When the magnet is moved in the opposite direction, the current flows in the opposite way, and the dial indicates a reverse current. If we move the magnet in and out repeatedly, the current will therefore alternate between flowing forwards and backwards. This is how AC or alternating current is generated. The current is continuously alternating in direction. If we move the magnet faster, a stronger current is generated. If we use a stronger magnet, then the current also increases. If we use a larger coil with more turns, then this will also generate a larger current. Instead of using a permanent magnet, we could use an electromagnet. As we move this in and out, it will also generate an AC current in the coil. But with the electromagnet, we can adjust the current and voltage to vary the strength of the magnetic field. This lets us control how much current is generated in the coil. Instead of moving a magnet in and out of a coil, we can generate a current much easier by rotating the magnet and placing the coils around this. The strongest part of the magnetic field is at the ends where the magnetic field lines converge. You can see the magnetic field lines by sprinkling iron filings over the magnet. With the magnet between the two coils, there is no current generated. But as the magnet starts to rotate, the strongest part of the magnetic field gets closer and closer to the coil. The coil experiences a changing intensity of the magnetic field. This will cause more and more electrons to be pushed forwards up until its maximum intensity. Then the magnet starts to move away from the coil, so the magnetic field begins to decrease, and so does the current of electrons until it reaches zero again. And now the opposite end of the magnet begins to get closer to the coil, and this pulls electrons in the opposite direction. This again reaches a maximum point and then decreases back to zero. And so, if we were to plot this current on a chart, we would get a sine wave with a current flowing in the positive and then the negative regions. This setup gives us a single-phase AC supply. But we have all this empty space between the coils, which seems a bit of a waste. So what can we do with all this space? Well, we can add more coils to create more phases and provide even more power. If we place another coil 120 degrees rotation from the first phase, this will give us a second phase. Why? Because the coil is at a different angle, so it will experience the change in intensity of the magnetic field at a different time. The current is therefore going to flow forwards and backwards at a different time. That gives us another sine wave, which occurs at a different time. We still have empty space here, so we can add another set of coils at 120 degrees from the previous set to create a third phase. If we use just a single phase, then for every rotation of the magnet, half the time the current is flowing forwards and half the time the current is flowing backwards. But with three phases, we always have a phase which is flowing forwards, and we always have a phase which is flowing backwards, which means we can utilize this to provide more power. Instead of having 3 separate coils and 6 wires, as the phases are always switching between forwards and backwards, we can connect the ends of the coils together. The current will then flow freely between each coil as it changes direction. Now we are producing 3-phase AC electricity, but all of our electrical circuits and components within the car use DC or direct current. So we need a way to convert AC to DC, and for that we use a full bridge rectifier. This is essentially just 6 diodes connected in pairs and wired in parallel. Diodes only allow current to flow in one direction, and they block the current in the reverse direction. With a single phase supply, for every turn of the magnet, current will only flow for half of the turn. The other half will be completely blocked. If we connected each of the 3 phases separately to a diode, then the current will flow or be blocked at different times. Therefore, we can combine these phases into a block of diodes, and only the phase nearest its maximum will be allowed to pass through. This gives us a slightly rippled DC output. To smooth this ripple out, we can connect a capacitor which will basically absorb electrons and then eject electrons automatically to maintain a constant output. This gives us a constant smooth DC supply. By the way, we have covered diodes, capacitors and power inverters in great detail previously. Do check those videos out, links can be found in the video description down below. Okay, so now we have a DC output. But if the magnet is connected to the engine and the car speeds up, then the magnet will spin faster, and that will increase the output voltage and current. We don't want that because it will kill all of our electronic components within the car. So we need a way of regulating the voltage. If you remember, we saw that by using an electromagnet, we can increase or decrease the electromagnetic field strength by varying the voltage. And by varying the strength of the magnet, we can vary the voltage and current generated in the coil. That's why the alternator uses an electromagnet, so that it can control the output. The car battery powers the electromagnet, although most modern alternators will use a diode trio, which converts the alternating current of the alternator into direct current and powers the electromagnet via a voltage regulator once the alternator is generating electricity. On the power supply of the electromagnet within the regulator, we find a component known as a transistor. The voltage sensor is also connected to the regulator. The transistor is a type of electronic switch, which can be turned on and off thousands of times per second by a controller. This can be used to control the amount of current flowing. If we imagine that the current flowing through the coil from the battery is at its maximum level for a given period of time, then we get 100% current and the electromagnet is at 100% of the strength. If the car speeds up, then the magnet will spin faster and that will increase the output voltage and current. But if we now control the switch so that electricity is only flowing for half of the time, then we get 50% of the current and therefore the electromagnet is only 50% of the strength. So, by measuring the output of the alternator and then varying the open and close times of the transistor switch, we can control the current flow through the coil and the strength of the electromagnet. This controls how strong the electromagnet will be, which affects how much electricity is produced. This produced electricity charges the battery. But now that you are all charged up, check out squarespace.com to create your own online web presence, which is packed with features to empower individuals to launch, share, and promote their own projects. There's powerful blogging tools to showcase your project photos, videos, and progress updates. You can easily schedule appointments for classes and sessions with team members or clients all through their inbuilt tools. And you can even collect payments or donations to help support your cause. Head to squarespace.com for a free trial. And when you're ready to launch, go to squarespace.com/engineering mindset to save 10% of your first purchase of a website or domain. Okay guys, that's it for this video, but to continue your learning, then check out one of the videos on screen.